let's recap what we know so far. So we have this idea of this thing called a vector space, and your hardest thing to do in this section is going to be let go of what you know and just work off of what the rules are. It's so hard to let go of intuition here. But a vector space, let's just recap that. It's a set of objects. Those objects are usually going to be mathematical type things, numbers and variables. Don't have to be. You have to have some way to add them and some way to multiply them by a scalar. And I put those two things in quotes just because addition, even if you are working with numbers, addition doesn't have to mean normal addition that we've always thought of. Add can be any way that you want to combine those numbers together. And same thing with scalar multiplication. It can be anything you want as long as you can sort of do it by 2 or by 5 or any scalar. But then to be a vector space, that set of objects has to meet 10 conditions. Right, that was these guys here. And as long as it meets those 10 conditions, it's joined the vector space club. We'll be able to do nice things with it later. So we had that idea. We also had the idea of a subspace. A subspace was also a set of objects, but those objects had to come from a known vector space. So you're just saying, hey, I've got a vector space up here. I'll pick that one and that one and that one, right? I'll take a few of the objects out of the vector space. So it's objects selected from a known vector space. And as long as those objects, that's this new set, as long as it meets 3 conditions, then it will be a vector space. So the basic idea here is 7 of the conditions will be inherited from the original vector space. Things like, associative addition, but there's 3 that we have to check that may have been broken by not picking all of the objects from the original vector space. And those 3 were basically closure under addition, closure under scalar multiplication, and the existence of the 0 vector. Because when you selected a smaller set of objects, maybe you left the 0 vector out. Or maybe you left out some things that you needed for closure. Right? But anyway, once those 3 things are met, then you can say, hey, my new collection of objects is also a vector space. Also will play nicely for all of this future theory that we're going to develop. So before we go too much further, it's worth talking about, especially when we talk about subspaces, it's worth talking about what are some known vector spaces. So let's do that. There's a few where you're not going to need to check all 10 conditions every single time, which gets old real fast, believe me. So some known vector spaces. I'm going to write them down, and then we'll talk about what each one of them means. Rn, Pn, and M. I forget what letters they usually use here. I'll use M by N. Okay, so Rn we're already pretty familiar with, I think. Rn are the columns that we've been using as vectors so far. So an example of Rn might be like R2. And that would be everything that looks like 1, 7, or 5, -3, or 0, 0, or all the rest, right? I mean, every R2. So all of R2 is a known vector space. So is all of R5 and R1, right? All of those are known vector spaces. I'll jump to the M. M by N. That would just be the set of all matrices of size n by n. So all 2 by 2 matrices are all 6 by 8 matrices. All those can be added. You can multiply them by a scalar, multiply them by 2, and those fit all the other 10 conditions, which we're not going to check here. We're just going to say that's a known vector space. And one more, the P sub n, I think that's, I don't know if you have a guess as to what P stands for. It stands for polynomial. So polynomials of degree n. So all second degree polynomials make a vector space, for example. So P sub 2 would be anything of the form ax squared plus bx plus c, where a is not 0, because otherwise then that's not a second degree polynomial anymore. But things like 3x squared plus 4x minus 2 and x squared and x squared minus 5, right? All of those, the entire collection of second degree polynomials works as a vector space. If you add two of them together, you get a second degree polynomial. If you multiply one of them by 7, you still get a second degree polynomial. You can add associatively, and all the other conditions are met as well. So let's get one more theorem, and then let's look at some examples. And we've got one more theorem that will give us one more tool about known vector spaces. So let's take a look at that. This is Theorem 1. It says if you've got some vectors that are in a vector space, they're from a known vector space, then their span is a subspace and therefore a vector space. Right. So let's get an idea about that. It's been a little while since we've seen the word span, but let's say we've got a known vector space, and I'll just keep it simple. We'll say R3. And let's take some vectors from that known vector space. Maybe I'll just choose 1, 2, 6. And 4, 0, 2. Those two by themselves, by the way, are definitely not a vector space. They don't contain the 0 vector. When you add them together, you get something that's not in the collection. That's not one of those two vectors. So by themselves, they're not a vector space. But think about span. When you talk about the span of two vectors, it means all possible linear combinations. So that means any constant times 1, 2, 6 plus any constant times 4, 0, 2. The claim of Theorem 1 is that this is a subspace of R3. Notice that it contains elements from R3. So 7 of the conditions are inherited automatically. We just need to check if the 0 vector is in there. And if I pick A to be 0 and B to be 0, if A and B equals 0, then what I will get is the 0 vector here. So the 0 vector is in there. Is it closed under addition? In other words, if I add two of these together, do I get something that is still an A plus, that's something that's still in this form, right? That's still in the span of 1, 2, 6 and 4, 0, 2. And yeah, no matter what A and no matter what B, I mean, that's the definition of span, right? So adding something like that to something else like that, it still gives you something like that. I know, all the technical terms, don't let that lose you. And finally, if I multiply something like this times a new constant, I still get something in that form. Right? I get a constant times one, and I get a constant times the other. I still get something that's in the span. Okay, so, and this was just sort of a check to see if what they were saying was really true. From here on out, we'll just say, I know it's true. If I have elements from a known vector space, the span of those elements is also going to be a vector space, also going to be a subspace of V. Okay, I know this is a lot of talking and a lot of weird theory. So in the next video, we'll take a look at a few homework examples, see what in the heck they want you to actually do with these things.